Good evening, all. Welcome to the problem solving session for the course Matlab programming for numerical computation. Let's wait for like 2 more minutes to see if there are more students to join the class, and then we'll start the session. So, whoever is there in the class right now, please do wait, and we'll start the session in like another 2 minutes. Good evening, all. Let's begin today's session. So, this week we'll be discussing about how to solve nonlinear equations. So, last week we had like saw problems like regarding how to solve a system of linear equations. So here this week we'll be trying to solve, just a second, we'll be trying to solve nonlinear algebraic equation. So if you don't have any doubts, please do unmute yourself. Like Mainak, please unmute yourself. Sorry, please mute yourself if you don't have any questions right now. So as we used to do in our previous sessions, this week also we'll be doing a quick recap of whatever we covered this week. So I'll be going through the theory and I'll be also showing the codes that has been shown to you in the recorded lectures. So in case you have any doubts in between, please to stop me and ask the doubts then and there. You can just unmute your mic and then ask me, or else if you can also put a message in the chat box so that I'll be addressing it when I see it. So going to the theory portion, after that we'll be doing few problems which are similar to the ones that you'll be getting for the assignments. So this will help you like this. You can consider this as like a practice session for solving your assignment problems. You'll be getting similar question for your final exam also. So let's start with the theory. So as I said earlier, this week we'll be doing nonlinear algebraic equation. Just a second. Let me just So this week we'll be doing nonlinear algebraic equations. So a nonlinear algebraic equation means you know what is a linear equation is, right? Linear equation is equation of a straight line. So it will be in the form of like y is equal to mx plus c, and you know it will be, sorry, it will be a straight line, right? It will be like a straight line, something like this. So now what is nonlinear? Nonlinear means you might get a curve like this. Like whatever is not a straight line, you can call it as like a nonlinear equation. So for example, this function that we can see right here, 2 minus x plus ln x is equal to 0. So this is the curve. This blue line that you see, this is the curve for this function, 2 minus x plus ln x is equal to 0. And when you say that it is equated to 0, this will have a solution. That is, for some value of x, this condition is true. Okay. So what happens is this is 2 minus x ln x. This blue curve is 2 minus x ln x. Okay. This curve that you see here is 2 minus x ln x. And what is x is equal to 0? This is the equation, and equal to 0 means that is this x is equal to 0. This line that you see here. Okay. Any point in the line, if you take it, it will be equal to x is equal to 0. So what happens when you equate these two lines? That is 2 minus x plus ln x equal to 0 means it is like we have this curve 2 minus x plus ln x. This touches your x-axis at certain points. Wherever it touches your x-axis, that is a solution for your system. So this you can see here, this touches at this point here and this point here, which means the solution, this problem has two solutions where x is equal to 0.1586 and x is equal to 3.1462. So these are the solutions that you see here. So now today the entire session, what we'll be trying to do is we'll be trying to look at like the various methods that will help you to solve a non-linear algebraic equation. So the question will be an equation like this, and as an answer we should be able to get this two values. Okay, so that's what we are trying to look at. As I said earlier, find the solution for any function f of x. What is meant by a solution? Solution is where the curve intersects the x-axis. Okay, so that's what we are intending to look at. Any doubts? Now we'll be looking at a certain category of methods. One is called as a bracketing method and other is called as an open methods. So just before going into the theory of this both method, I'll just give you a quick understanding of what these two methods are. So bracketing method means you will have to create a bracket. So bracketing method means you will have to create a bracket. For example, you know your solution is like 0.15 something, right? So what you have to do is you have to create a bracket. When you start the program, you will have to say that, okay, find the solution that falls between x is equal to 0 and x is equal to 2. So this is the bracket, 0, 2. This bracketing method will try to find solution that falls within this bracket. So that's what bracketing method does. So in bracketing methods, we'll be discussing a method which is called as bisection method. Now the second category of method is open methods. Instead of giving a bracket of values, I'll give an initial guess for the values. Okay, so this is similar to the iterative methods which you have seen in the previous weeks. So I know that my value is like has to be some 0.15 something. So to begin with, I'll start with x is equal to 1. So from x is equal to 1, I'll keep improving. I'll get a new x value. Again, I'll be getting a new x value. And finally, when I keep going like this, I'll land where x new is equal to 0.15 something. Okay, this goes like that. So this is called as an open method. You start with an initial guess, you keep improving your guess, and finally you land into your solution. So this is called as open methods. If you're giving a bracket, that's called as a bracketing method. In open methods, we'll be discussing two kinds of method. What is fixed point iteration? And the other one is a Newton's method. Apart from this, we'll be also discussing some inbuilt Matlab functions which you can work with. That is called the F0 and Fsolve. So this is what we'll be covering this week. Now moving on to the first method, that is a bisection method. Okay. So in bisection method, what you have to do is, as I said, it is a bracketing method. So initially itself, you have to give a bracket. So for example, I have to find this value. Imagine that I have to find this value here. Okay. That is 3.1462. I need to find this 3.1462. Initially, I'll give you two values. The two values are XL and XU. So for right time being, I'll give XL is equal to 2 and XU is equal to 5. This is X lower limit and X upper limit. Okay, 2 and 5. I need to find a value that falls between this 2 and 5. So that's what I'm trying to do. Now, when you start the bisection method, one thing you have to keep in mind is that you can give any initial guess, but the condition is the function value at this initial guesses should have opposite signs. That is, you have this function 2 minus x plus ln x. Okay. Now, this is your function f of x. Now, what you have to do is you have to calculate f of 2 and you have to calculate f of 5. Okay, sorry, f of 5 here. Let me just. Yeah, you'll have to calculate f of 2 and f of 5. Okay. Now what happens is if f of 2 is positive, f of 5 must be negative. So in this case, what happens? What is f of 2? So 2 comes somewhere here, right? So if you take 2 somewhere here, f of 2 is positive value, right? This is your f of x side. So this is your f of x and this is your x. So f of x is somewhere here. So this is positive. F of 2 is positive. F of 2 is positive. Now f of 5. So 5 is somewhere after here. So this is 3.146. So let me imagine let's 5 is here. Okay, 5 is here. So what is the value of 5 here? F of 5 is, you can see it's a negative value, right? So f of 5 is a negative value. So you have to choose bracket in such a way that your one value is positive, other value is negative. It can be other way around also, okay? F of 2 could be negative and f of 5 must be positive. Like whatever it is, you will have to have opposite signs for your initial guesses. That's the first thing you have to keep in mind. So once you have chosen your XL and XU in such a way that the function values are of opposite signs, you need to find the new x value. So the new x value is the midpoint of the previous two guesses. Okay. So the idea is first I take this red dot here. This is my first guess. This is my first guess. Okay. You can see this is having a positive value and this is having a negative value. I've taken two guesses like that. Now what I do is I have to calculate the midpoint of these two guesses. That is this green, this one. This is the midpoint. Okay. Now what I do is I calculate what is the function at this point. So if you see what is the function at this point, that is again negative value, right? This was also negative, but this was positive. So when I get a negative value, what I get is the previous negative value that I have, right? I'll remove this and I'll make this as the bracket. Just a second. Okay. So my first bracket was this. Okay. First bracket was this. Now I got the green value. You know, the green is also negative value. So I, I remove this bracket. Instead, I create a new bracket. That is this. This is my new bracket. Okay. Now again, I calculate what is the midpoint at this midpoint of this bracket. What is the midpoint of this bracket? That is this green. Okay. What is the value at this green point? I see. And again, this is positive. So what I do? I remove the previous positive bracket. I remove this one. And now I have a new bracket. Let me just draw the new bracket. So the new bracket is this. Okay. This one I removed. And now I have a new bracket. This one is my new bracket. And the negative bracket remains as such. Okay. So if you see, your first bracket was this big. Okay. Your second bracket is only this big, the green one. And your next bracket is the smaller one. Right? So what we do is we start with a larger bracket. As the procedure goes forward, what happens is your bracket becomes smaller and smaller. See, your bracket initially was bigger, then you get a smaller bracket, then you get a smaller bracket. Finally, what happens is this bracket, both the ends will collide into a single point. That's when you reach the solution. Okay, do you have any doubts here so far? Should I explain this procedure once again? I'll just tell you. initially choose a point in such a way that, so in this graph, you'll have to choose a point, one in the positive direction, another in the negative direction. So your bracket is this big. Now you take the midpoint. Okay, imagine the midpoint is here, and you can see the midpoint again, it is positive. So you remove this bracket, and instead you get a smaller bracket. Again, you take the midpoint of this, again you get a smaller bracket. So it goes on like that until you collide into a single point. That is when you land to the solution. I hope this is clear. Any more doubts? Okay. So that's what we do. We create a new x new point based on the guesses. You calculate the value of that x new, and you replace either the xl or xu based on the based on the sign of this function value. Okay. Yeah, that's it. Now, what we'll do is we'll look at the code, Matlab code that is doing this program. Just a second. I hope we can see Matlab right now. So this is how the function will look like. So this is how the function will look like. So first, this script is written to solve the function 2 minus x plus ln x. Okay, just a second. Okay. This function is made to solve the function 2 minus x plus ln x. Now what you have to do is I have to choose a bracket. So time being, I am choosing the bracket 1 and 4. So you know there are two solutions, that is 0.15 something and then you have 0.3 something. So when I'm giving like 1 and 4, sorry, it is not 0.3, it is 3 point something, right? So when I give this bracket 1 and 4, I should be landing in this solution because the 0.15 is not between this bracket. Okay, so I'll not be getting this solution. I'll be only getting the 3 point something, that solution. Now what I do is I calculate the function value at xl. xl is 1. I calculate the function value at xu is 4. Now I have to ensure whether the signs are opposite. For signs are opposite, what do? You have to just multiply the both function values. If it is greater than 0, it means that the signs are the same. Okay, that's not what we want. Okay, so if this is the condition, we say that, okay, error, we display an error message. What is the error message? Initial guesses should have different signs. Okay, so if the initial guess both are positive, positive multiplied by positive will give you positive. If both are negative, you will be getting multiplication. Again, you will be getting positive. So that's the condition we use here. If one is negative and other is positive, the multiplication will give you negative. Okay, so this is the condition that we use here to just check if both the values have different signs or not. If the functions have different signs, then we proceed into the solution further. So now what we do is, if we have the solution, if we have the initial bracket correct, what we do is you can run it for certain iterations, or else you can use a while loop and you can track the error. That is also possible. So for the time being, let's run the for loop for like 50 iteration. Max iter is 50. I'm running the for loop from I equal to 1 to max iter. Now what I do is I calculate what is the error. This is just to track how my algo is going. So my error is the absolute difference between the two brackets. Now my new x new is what? That is a midpoint of the two brackets. That is xl plus x new divided by 2. That is a midpoint. Now what I do, I calculate what is the function value at the midpoint. So this is the function value at midpoint. 2 minus x new plus log of x new. Now I have to see if x new is having sign similar to fl or similar to the fu. So what I do, I just do the multiplication. If fl and fnu is greater than 0, if this condition is true, what is the meaning? This condition means that fl and fnu have same signs. Okay, this means that fl and fu have the same signs. So if that is the case, what will happen? You will replace the xl with xnu. So xl becomes xnu and fl becomes fnu. If this condition is not true, what does this mean? They have different signs. If this condition is true, what happens? You replace XU with X new and FU with F new. Is this clear, the code? Now, once you've replaced the bracket, again, this loop will continue with the new XL and X new. You keep going until the 50 iteration is done. So now let me run this code and show what will happen. So now you can see that, see, XL, you started with 1 and 4, it got replaced. Okay. Now finally you can see that XL and X new has come to the same value, 3.1462. So what is the midpoint value? It's the same value. So the answer is 3.1462. The second root, that is 3.1462 is the root that you get. So if you see the error is what? Error is the difference between your upper limit and the lower limit. That is very, very small. It is of the order of e raised to minus 50. Okay, so that's how you get to the solution using the bisection rule. First, you choose the bracket, you keep on shortening the bracket. Finally, you will be getting a single, it will collide into the bracket, will collide into a single value. So here we have got 3.1463. Now, if I want to get the first value, that is 0.15, what I do, I change the bracket. So I'll keep x lower to be 0.01 and x upper to be 1. Let's see what will happen. Let me just clear. Okay. And run it again. See, now my x new is 0.1586. That is the second root. So what I gave is I gave a lower value of xl 0.01 and upper value of 1. Okay. Another question will be like, can I use 0. Can I use 0 here? Can I use a lower limit 0? What will happen? Let me calculate what's the function value at 0. That is 2 minus 0 plus log of 0. Do you have that value? No, it will show, sorry, log minus. Okay, it is like infinity. So that is not possible. So that is why you can't give 0. You have to give a slightly different value than 0. So what I did is I have to get 0.15 something. So I gave the bracket 0.01 and 1. And I landed into the first root, that is 0.1586. Is this clear? I hope this is clear. Okay. Now going into the next part of the session. So first we have completed the bisection method. Next is how to use the inbuilt Matlab function, that is F0. So F0 also is like it's a direct inbuilt Matlab function, just that you need to know how the syntax looks like and you need to know how to give the inputs to this Matlab function. So Matlab function F0 is used to solve nonlinear algebraic equations in a single variable. Keep that in mind, it should be a single variable. Now, next is we use bracketing method. The underlying mathematics of this F0 is the bracketing method itself. So what is the syntax? Syntax is like this. Xsol is a variable that saves the solution. You can give any other variable name. It's just a name, okay? It's just a variable name. You can give any other name instead of Xsol. F0 is the function name. This is very important. This F0 name is very important. Now what happens is this is called as an anonymous function. We have done it in the previous sections also. What happens is you give a random function name which has this 2 minus x plus ln x saved. Okay, you have the function which saves this format and you have to say that x is the variable we are trying to solve for. So this x and this x should be the same. Okay, it should be x itself. If your variable is y, here you have to write y. If you are writing here y, it has to be y there. And then you give the initial bracket. X0 is what? X0 is the bracket. You will give XL semicolon XU. So this is like a column vector. You give the lower limit and the upper limit is the value for the initial bracket. Okay, it's a value for the initial bracket. So now what we do is we'll try to see how to solve using F0. Just a second, I'll just show the MATLAB code. Okay, so this is how the function looks like. First, we have to, so whatever I've commented down here, that is the comment that we have. Okay, one is the solution, whatever variable I have. Then I call the function f0. I'm solving for the variable x. And this is the function that I'll save the 2 minus x plus ln x format. I'll show you that again. Then the bracket I'm trying to solve for is 1 to 4. Okay, it has to be 1 semicolon 4. It is like a, so it is a column vector. See, it's a column vector 1 and xl and xu, lower limit and upper limit. Now, what this fun for bisect does? Fun for bisect looks like this. It's a function. You write the function keyword. It has an output, and the fun for bisect is the name. It takes an input x. When it takes an input x, it calculates 2 minus x plus log x, and whatever value I get out of it, that is called as a f val. That is the output of this function. So this is how I should write it. This is a nonlinear function evaluated at a point x. Whatever value that I get, that will be the output of this function. Now, how do you solve this? I'll just clear CLC and I'll just run this equation. This is the syntax I have to run it. Okay, I get the solution 3.1462. Now I'll just change the limit. Let me do 0.01 and 1. And let me change the bracketing. I get the other solution 0.15859, so and so. Now, if you have any doubts how to work with F0, you can type help F0. See, you will be getting F0 is a single variable nonlinear zero finding method. It's trying to find the zero of a function near x0. Okay, so this is how we work with it. There are like syntaxes also given to you. Okay, I hope this has been helpful. So now going on to the next part. If you have any questions, please do ask. Okay. So now next we have done with bracketing methods, and the next one what we will be dealing is the open methods. Okay, so it will be like an iterative procedure where you start with an initial guess, you keep improving the initial guess until you land to the actual solution. Okay, so now you have a function which is of the format f of x is equal to 0. The first thing what you have to see is you have to convert that into a format of x is equal to g of x. There are several ways in which you can do that. So first we look at that portion. So the first function you are solving, it is in the form of 2 minus x plus ln x. So this part is the f of x. Okay. You have to rearrange it in such a way that you have to write x as the function of x. This has to be written in like that. So this function will be something, a different function. Okay. So you have to write in the form x is equal to g of x. So you can arrange it in two different ways. You think of taking this x to the other side. Now it becomes x is equal to 2 plus ln x. So now you can see x is there in the left hand side and x is there in the right hand side. That is one way of doing it. Other way is you do is you take the ln x to the other side and you take the exponential of it. So it becomes 2 minus x is equal to ln x. Taking the exponential, it will be e2 minus, sorry, minus sign is there. So just a second. Okay, let me do the first one carefully, just a second. So 2 minus x plus ln x is equal to 0. What you can do is bring the x to the other side. So you will have 2 plus ln x is equal to x. That is one equation. Next equation is 2 minus x plus ln x is equal to 0. I take this to the other side. So ln x is equal to x minus 2. Now what I do, I take the exponential. X is equal to exponential e raised to x minus 2. Okay, so this is the second way of writing. So this is the first equation and this is the second equation. Is this clear how I got the two equations?
Yes, ma'am.
Okay, yeah. So once I've got the two equations, what I have to do is I have to start with an initial guess. So this initial guess, it is like a trial and error method. Okay. So the thing is for this method to to get you to the actual value, you need to give a good initial guess. That is a problem with such methods. But if you give a good initial guess, it will land you to the values you need. Okay, just a second. Let me just check the. Yeah. Okay. Now what you do is, so I'll take for the example of the first equation. Okay, that is x minus x is equal to 2 plus ln x. Let me assume the initial value condition. Let me assume initially x is equal to 1. I'm just assuming x is equal to 1. Now what happens is I substitute this x is equal to 1 here. I get the new x value as 2 plus ln 1. Okay, that will be my new x value. Once I got the new x value, I put that again back into the equation. So what happens is using 1, I get a different value, 2 plus ln 1. Again, I put this value, so it becomes 2 plus ln 2 plus ln 1. Like that, I go forward and I land into a single value. Now, how to see whether you have landed at the single value? You can calculate the error. What is the error? Error is the difference between in the two current, in the consecutive iteration, what is your x value? So that is x new minus x old. Take the absolute of it. Okay. So this is your error value. When the error is below some 0.0001 or something, you can say that, okay, you have reached to the solution. So this is how you have to work with the fixed point iteration. I'll show you the Matlab part. Just give me a second. So this is how the Matlab equation looks like. So the first I'm solving it for the first case. Okay, 2 plus ln x. If that is a function, what will I do? Now what I do is I have the different initial guess. So first I'm seeing for initial guess. Let me try for x is equal to 1. Okay, I'm just making x0 is equal to 1. That is my initial guess. Now I can run it for 50 times, or else I can keep an error tolerance of 1 e raised to minus 4. Now what I do is initially my x value is the initial guess, and my x old value also I'm just initializing into the initial guess. Now what I do is I run the for loop. What I can do is I can run the for loop up to 50 iteration, that is 1 is to 50, and I calculate the new x value. X is equal to 2 plus log x, and you know this x is this value x0. Okay, you get the new x value. Error is nothing but absolute difference between x and x old. Now what you do? You have to reinitialize x old. X old is equal to the new x. So this goes on until the error is like accumulated. And when you can also add a break statement. If any error of a particular iteration is less than the tolerance level, you just break. When you put break inside a for loop, what happens? It will break the entire loop. It will come out of the loop. Okay, this entire thing will be broken when you do the break. So it will come out of the for loop. So apart from this, you can also use a while loop. You can keep the error tolerance, this thing here in this sentence, and you can use a while loop. Okay, that is also completely fine. Okay, so this is how we work with the fixed point iteration. Let's see what solutions you will be getting. Okay, so let's give me a second. Clear. CLC. When my initial value is 1, so here you can see the values here. Though the initial value is 1, what happens is, though the maximum iteration is 50, my loop only ran 11 times. Why? At the 11th time, the error went below the threshold. So that is why I broke out of the loop. Now let me see the error. So every iteration, I'm saving the error. So as you can see, in the first iteration, my error value was 1. In the next iteration, error value reduced to 0.69, then 0.29, 0.1048, 0.03, 0.01, 0.0035, so on. Okay, then it became of the order of e raised to minus 0.5. And let's see what is the solution I'm getting. When I started with 1, I landed into the solution 3.1462. The second route I got. Let me change the value to 0.01, initial guess to 0.01. You can see the loop ran for 12 times. It didn't go till 50. It only ran till 12 times. And the solution I'm getting is this. Okay, it has a real part and an imaginary part. So this solution, like whenever you have a imaginary solution, it's like you can say that, okay, the solution has not converged properly. Though it is a very small imaginary part, it's like the solution has not converged properly. Okay. So what I do is I give a different initial guess. Let me give a different initial guess 4. Run the solution again. It only run for like 9 times. And my solution is 3.1462. Again, I got the second root. Now again, changing the initial guess to some 40, a different higher value. The loop ran for 11 times and my x value is again 3.1462. So in the first case, in the first, so that is in this, when you're using this condition, that is g of x to be 2 plus ln x, whatever initial guess I gave, I always landed upon the second solution. Okay, this depends on your problem. You can't say that okay, one solution always lands into a one root. Like you can get multiple roots also. Okay, so but in this case, what happened is when you're using this functional form, you're always landing in the second solution. We are not getting the first root. Now let's see the second solution. That is, why don't we use this 2 exponential x minus 2? So for that, everything is the same, just that here you have to make the change. Instead of 2 plus ln x, you have to write exp x minus 2. That's only change here. Again, you can repeat the exercise. Here it becomes exponential x minus 2. Now, using 40, let's see what solution you're getting. Using 40, I'm not getting anything. It's like infinity. Okay, this is diverging. So let me use the initial symbol guess. X is equal to 4. When x is equal to 4, I am getting, it ran for all maximum iterations and the error has not converged. Again, I'm getting infinity. So this has not converged. Let me take a different initial guess. X is equal to 1. Again, when I run the solution, I am getting the first root, 0.1586. Okay, so now I change the initial guess again to 0.01. Again, I land up in the solution 0.1586. What if I use a value which is very close, something like 3 or something to the second row? What will happen? Again, I'm landing on the first row. So what happened is your first equation always took to 3 point something value. Whatever values it took to the 3.1. Your second equation, what happened? In some cases, it diverges. You get infinity, or in some cases, you get the solution 0.158. Okay, there are two different behaviors. So what happens is a function can be written in multiple ways. The way I write will be different from the way some of you write. So it is different. Okay, you can write the function in any way you want. You can give the initial guess also in any way you want. Okay, so this is very, very important. The way you write the function and the way you give the initial guess, your solution will depend on these two factors. Okay, so that is completely dependent on the problem and completely dependent on the person who's solving the problem. Okay, so is this clear? Any doubts? So I hope the fixed point iteration is clear to you. Now let us move on to the next section. So next section is also an open method. This is called as a Newton-Raphson's method. So let me just check the time. Yeah. So Newton-Raphson method is also an iterative method, just that here you have a fixed functional form. Okay. So if you're trying to solve for this function, f of x is equal to 2 minus log x, what you have to do is first you have to calculate the derivative of this function. Derivative of the function is f dash of x. What is this derivative of 2 is 0, derivative of minus x is minus 1, derivative of ln x is 1 by x. This is the derivative of the function. Now, as I said, this is a iterative procedure. So you have to start with an x, you have to get the new x, you have to again replace the new x, again it goes on like that. So now this is a functional form you have to start. That is, I start with an x value, and the new x value is the old x value minus the function at the old x value divided by the gradient at the old x value. Now I get the new x value. Again, this I resubstituted here. I get xi plus 1. So what will be xi plus 2? That will be xi plus 1 minus function at xi plus 1 divided by derivative at xi plus 1. I get xi plus 2. Like that, I keep going forward. I have to calculate the error. What will be the error? Error will be absolute difference between x old and x new. this has to go beyond a certain threshold. That is when you say that this method has converged. So out of all the methods so far we discussed, this method is having a faster convergence. This method is said to have a, what you say, it's called as a quadratic rate of convergence. What is meant by this E means E is the error. Okay. So what we say is that if the error in the ith iteration, okay, error in the I plus 1th iteration is square of error in the ith iteration. So imagine that in the first iteration, you are getting an error of 0.1. In the second iteration, first iteration, you're getting 0.1. In the second iteration, you will be getting the square of 0.1. Okay, that is 0.01. So as the iterations progress, your error will be drastically reducing. And this, since it is 2, the power is 2, since of that, we call this as quadratic convergence. Okay, quadratic convergence because of this 2 here. You can prove this also how this 2 is coming here. So this method also, just like the fixed point iteration, you have to have a good initial guess. The function form is fixed, but the initial guess is very, very important. So the fixed point iteration, it has a linear rate of convergence. Okay. But fixed Newton-Raphson method, it has a quadratic rate of convergence. This is faster than fixed point iteration. Is the method clear? I'll show the code now. Any doubts so far? If not, I'll show the code. Just a second. Yeah. This is the code. So this is a function I'm trying to solve for. Okay. This is a function I'm trying to solve for. That is 2 minus x plus ln x. Just a second. That is 2 minus x plus ln x. I'm starting with an initial condition x is equal to 2. I can start with any condition. Right now, I'm just taking x0 is equal to 2. I can run up to maximum iteration. I can also keep a tolerance level. So what I do, initial x value is x0, x hold is also x0. I run up to 1 to max iter. This is my function value, and this is my derivative value. I get f and df. Okay. At x, this is my function value. My derivative value is minus 1 plus 1 by x. Now, this is my update formula. As I said, this will be the old x minus the function value divided by the derivative value. I'll get the new x. Now what I do? Now I have to see what is the error value. Error is what? Error is difference between the new x value and the old x value. After calculating error, I update the old x value. Now the error, if it is below the tolerance level, again I break. Again, when I break, what happens? It will be out of this loop. I'll be reaching here, completely out of the loop. Okay. So that is how I update. This is the update formula. This is the only difference, this equation. This part is the only difference between the fixed point iteration. Only these 3 lines are different. Okay. The rest remains the same. So far, any doubts? Now I'll be running this code. Now for x is equal to 2, what we'll do is, we have this fixed point iteration formula, right? And the equation was 2 plus log x. So let me just change this. Instead of ln, natural logarithm in Matlab is written as log. Okay. So now what happens is I'm giving an initial guess x is equal to 1. Here also I'll give the same initial guess x0 is equal to 1. Okay. Fixed point iteration, when I run, it took 11 iterations. Okay. For the convergence of tolerance level e raised to minus 4. 11 iterations. For the same iteration, let me see what will happen if I'm using Newton-Raphson. Okay. This is not converging because when x is equal to 1, because you can see here df. What is df? So for x is equal to 1, it will be minus 1 plus 1 divided by 1, it is 0. Okay. and your formula is f divided by df. So what happened is when I use x is equal to 1, df is equal to 0, and I have a term in the equation f divided by df. You can't divide a number by 0. You can't divide a number by 0. This will reach to infinity. Okay. So it's very important whenever you're giving an initial guess in Newton-Raphson, your gradient should be valid. It should not be 0. You should get a non-zero gradient for that initial value. So let me just try for a different initial value. Clear. CLC. Now I'm giving initial value 2. Okay. In the fixed iter also, I'll give you 2. Now I'll run the fixed iter. For 2, I run like 10 iterations. I land on the solution 3.1462. In the same Newton-Raphson, when I run, I reach the same solution in 4 iterations. See, it is faster than fixed point iteration. I only require 4 iterations. And my x value is again 3.1462. So this is what I said. Newton-Raphson is faster than fixed point iteration. Now, if you want to know how this power is coming as 2, how is it quadratic convergence, what you can do is, you can plot. So earlier we had seen that E, just a second. So we have seen this relation E I plus 1 is equal to E I square. Okay. Earlier when we were seeing the order of accuracy and all, we have seen how to get this value. What you have to do is you have to create a vector. You have to take all the I plus 1 iterations errors. You have to also take the I iterations errors. So for example, if you are running 5 iterations, so total iteration is 5. If total I is equal to 5, okay, you have iterations I is equal to 1, 2, 3, 4, 5. Then your I plus 1 will be 2, 3, 4, 5. Okay, so far. So what happens is, let's avoid this one. You plot this portion. Okay, this is your EI. This is your EI plus 1. So you have to just plot the errors. Now what happens when you plot the errors, it will not be clear. So what you do is you take the log. When you take the log on both sides, what happens? You will have log here and this 2 will come in the denominator. So here, okay, you'll have log here. So basically you will have log of EI plus 1 is equal to 2 times log of EI. So what you have to do is just plot this portion and plot this portion and calculate the slope of the straight line. It will come out to be 2. Slope will be equal to 2. That's exactly what we're doing here in the code. What happens is in the error, you can see this is how the error looks like. It has like some 10 iterations or something. I'm only going for the first 4 iterations. What happens is my first error is 1, 2, 3 iterations. Corresponding to that, EI plus 1 will be 2, 3, 4. Okay. Now what I do, I plot the log of the previous iteration versus a log of the current iteration. Let me plot it here. I am getting a straight line like this. Okay, this is a straight line that I get. Previous iteration versus the current iteration. Now I can calculate the slope. If you want, I can directly go and click this point and calculate the slope. Y1 minus y2 divided by x1 minus x2, or else numerically I can do is log of the current end value minus log of current end's first value divided by log of the previous end's end value minus log of previous end's first value. Basically, take the slope of the curve and you will be getting, when I evaluate this, I'll be getting slope is equal to 2.08 something. So that is what you will be getting. It will be the error value is this. Now the same thing if I do for the fixed point iteration. We'll do that also. Just give me a second. So for the fixed point iteration, what I do is, here also I have errors, right? Here also I have errors. So I'll run this fixed point error once again. Now I've got like a different error. I've run it for like 10 iterations. Now I'll write hold on the same plot and I'll run this. Now what happens is, this is the error that I get for the fixed point iteration. So you can see the slope here is 1.14. It is less than 2. The blue line is for the Newton-Raphson. This blue line is for Newton-Raphson, and this line is for fixed point. You can see this is having slope is equal to 1 and this is having slope is equal to 2. This is having quadratic convergence. You can see how fast the error is dropping, and this is having linear convergence. Okay. I hope this is clear. Any more doubts? If not, let's move to the next topic. So that is using the F-solve. So F-solve works with the Newton-Raphson's principle. You have to just learn to know the syntax of the F-solve, how to give the input and how to take the outputs. That's the only thing. Syntax is very, very similar to F0. You have a variable to store the output values. Fsolve is the keyword that you use. The function variable you are trying to solve is for x, and this is a function that saves the 2 minus l. What is it? 2 minus x plus log x, right? This function will be saved here, and this for here, instead of the bracket, you have to give the initial guess. Okay, so you have to give the initial guess. With fsolve, you can solve for one equation and you can solve for multiple equations also. That will come to that later. Okay. Now we'll see the example with fsolve. Just give me a second. Let me just share Matlab. Let me just close all this. Clear. CLC. Now what I have to do is, okay, this is a function. The function has been already written, fun for bisect. I'll see. This we have already seen actually. See, if you give an x value, you will be getting the function 2 minus x plus log x. That's what this fun for bisect does. So the syntax is this. Okay, when I give the initial guess 1, we'll see what happens. So fsolve, I'm solving for the variable x. Fun for bisect has equation, and I'm giving the initial value 1. It will show you no solution found. Why solution is not found? Because the gradient is 0. So the same problem that we had with the Newton-Raphson will come here also, because the gradient is 0 at x is equal to 1. So now what I do, I give a different initial guess. Let me give 2. I got the solution 3.146. Let me give a value 0.5, which is close to the first solution. I'll be getting the first solution 0.1585. Okay, so it's like I get the closer value. So this is what happens when I use the epsilon. It uses a Newton-Raphson's equation itself. So here also you have to ensure that the initial guess should have a valid gradient. It shouldn't be 0. Is this clear? Any doubts?
No, ma'am.
Okay. Now let me go back to the presentation then. So this is what an explanation. Epsilon or Newton-Raphson method cannot solve with an initial guess that has a local minima or local maxima. This means that the local minima and local maxima, the gradient will be 0. Okay. This means that the f dash at that point, that is the gradient is equal to 0. That is not, should be, that initial guesses should not be taken. Initial guess, which is to the left of the maxima, gives the first solution. So that is, this is the solution that I have. When I give 0.5 here, something here, I landed in the, sorry, not here. Just a second. 0.5 is here. When I gave 0.5, I got this solution. When I used a value 2, I landed up in this solution. When I use the value 5 also, I'm landing up in this solution. Okay, so different initial guesses will take you to the different solutions when using Fsolve. Now moving on to the next topic. So far we just saw one solution, right? One nonlinear equation. So now we have like 3 set of equations. We have here 3 set of equations. three set of equations. This is linear, but this is non-linear, this is non-linear. Basically, you have like three set of equations. You can solve it using fsolve. It's just that in fsolve, you saw there are two portions, two important portions. One is the function name, function. This function should give the three functions in column. It should be first column, second column, third column. It should be a single column vector. Three functions should be given. And the initial guess. Initial guess, earlier it was a single value. Now that should be a column vector. Okay, this is the initial guess for x, initial guess for y, initial guess for z. Function should be a column vector, initial guess should be a column vector. Okay, that's how we need to define this problem. So let me go to that. So first, let us see how to solve using, sorry, I just quickly went into this. First, let us see that how to solve using fsolve. So let me just share Matlab. Okay, this is how we need to solve. So this is the function. Instead of the earlier function, we have the function name called as Lorentz system. It has a variable x. This is a column vector. In the column vector, the first value corresponds to x, second value corresponds to y, and the third value corresponds to z. Once you have extracted x, y, z from this column vector, you have to write the function value. Remember, the function value should also be written as a column vector. So that is why you can see first row, first column, second row, first column, third row, first column. So there is only one column here. There are three rows. The first row is the first function x minus y. This is the second function and this is the third function. You have written functions also as a column vector, right? Now let me give the initial guess. As I said earlier, initial guesses should be given as a column vector. This is my first initial guess, 1, 1, 1. My solution that I get is, this. You can see that solution found, equation solved. Solution is 1.732, 1.732, 1. The solution has like three solutions, okay? It is, the three set of solution is 1.732, 1.732, 1. Other solution is minus 1.732, minus 1.732, 1, and other is zeros. Now let us try with a different initial guess. This is my different initial guess, minus 1, minus 1, 1. When I try to solve this solution, I get the other solution, minus 1.732, minus 1.732, 1. Now let me use a different initial guess. Okay, this is minus 1, minus 1, 0. Again running, I'll be getting something value which is close to 0. Okay, I'll be getting something close to 0. It's not exactly 0 because it has certain tolerance criteria. For example, stopping criteria details is this. If you click on the stopping criteria details, you'll get it. Equation solved. Sum of the square function is r. It is less than the function tolerance. Okay, relative norm of the gradient is less than this, and the tolerance level is e raised to minus 0.6. That is your error value that you found, right? X minus x sold. That when below this error value e raised to minus 0.6. That's why it got converged. Okay. So that's how we use the fsolve for multiple equations. Now let's see how to use Newton-Raphson method for this multiple equations. So that is this equation. Okay, just like we solved for Newton-Raphson. Earlier Newton-Raphson, what was the equation that we do? Just a second, let me just annotate. Just a second. So earlier Newton-Raphson, your xi plus 1 was taken as xi minus f of x divided by f dash of x, right? Gradient. Now, when it comes to multi-dimension, xi is a column vector, I plus 1 is a column vector, xi is also a column vector. Now, instead of x, f of x will be a single value, it's a scalar value. But instead of this, instead of f dash of x, you will have the Jacobian. Now, we need to know how to write a Jacobian. Jacobian is the derivative of the function with respect to, sorry, f of x is not a scalar value, right? F of x has three functions. So it is not a scalar value. That will be also a column vector. Okay, three functions will be there. It's not a scalar value. Sorry for that. Now Jacobian matrix has to be written. Jacobian matrix is like written like this. So I'll just show you the matrix. This is how the matrix looks like. So the first function derivative with respect to the first variable. First function derivative with respect to the second variable x2. Now first function derivative with respect to the third variable, so on. Now the next row will be second function derivative with respect to the first variable, second function derivative with respect to second variable, second function derivative with respect to the second variable. Now this is the last function derivative with respect to first variable. So on you'll write, and the last entry will be last function derivative with respect to the last variable. This is clear. Should I repeat it again? I can write it once again very neatly. So if you have the Jacobian matrix and you have three functions and three variables, it looks like this. Okay. D of f1 divided by dou x1, d of f1 divided by dou x2, d of f1 divided by dou x3. Three variables. Now, second function f2 divided by dou x1, dou f2 divided by dou x2, dou f2 divided by dou x3. Now, second function is done. Now, third function dou f3 divided by dou x1, dou f3 divided by dou x2, dou f3 divided by dou x3. This is the Jacobian matrix. Once you've got the Jacobian matrix, what you have to do, you have to take the inverse of the Jacobian matrix and pre-multiply. This has to be multiplied like this only. Matrix, then the f of x, and it has to be subtracted. That's how you get the new set of x values. Now, this is a system that we have, x minus y. This is f1, this is f2, and this is f3. Okay, f1 derivative with respect to x is 1, derivative with respect to y is minus 1, z is not there, so it is 0. Now this is f2, derivative with x is 2 minus z, derivative with respect to y is minus y, derivative with respect to z is here, minus x. This is a partial derivative, so I hope you know how to take partial derivatives. Now the third function, derivative with respect to x is y, only y is there, okay? Derivative with respect to y is, now x becomes a constant, so x is there. Derivative with respect to z is minus 3. So this is how you get the Jacobian. You got the matrix. Okay, any doubts so far in
Ma'am,
getting the
could you
Jacob?
repeat the Jacobian part again?
Did you understand this part? This formula part, did you get? This portion? This
Ye-
portion?
Yes, ma'am.
Uh,
Just the partial differentiation part.
okay. I hope this portion you got. This portion you got, right? This portion, or should I repeat it again?
Yes.
Okay. Okay. Now the partial differential part comes like this. Imagine you have three functions, f1, f2, f3. Jacobian matrix comes like this. Let me just clearly write here. Okay. You have the first function derivative with respect to the first variable. So in this case, it is first variable as x. Now the second function derivative with respect to the second variable, here it is y. Now the first function, but derivative with respect to the third variable. Now this is dou f2 divided by dou x, dou f2 divided by dou y, dou f3 divided by dou z. Sorry, f2. I made a mistake. Now you go to the second function, third function, sorry, f3 divided by dou x, dou f3 divided by dou y, dou f3 divided by dou z. This is for f1, this is for f2, and this is for f3. Column wise, if you look, this is for x variable, this is for y variable, and this is for z variable. Is this clear?
Yes, ma'am.
Okay. Now what you have is, you have the function x minus y. So when you take the partial derivative with respect to x, you will consider y and z are constants. That's how you calculate partial derivatives, right? So with x, what is a derivative? The coefficient is 1. So 1. With respect to y, what is the derivative? Coefficient is minus 1. So minus 1. And z is not there. Because of that, you have the derivative to be 0. This is first function, dou x, dou y, dou z. Is this clear?
Yes, ma'am.
Okay. Now the second row is second function. Second function with respect to x, what will happen? 2 minus z will come because z is a constant. 2 minus z. Now, with respect to y, minus 1 is a coefficient. So minus 1. With respect to z, what happens? Only this is there. Minus x becomes. So this is for with respect to this portion. This portion. Now the third line is for function 3. With respect to x, the variable is the coefficient is y. With respect to y, the coefficient is x. And with respect to z, the coefficient is minus 3. Now is it clear?
Yes, ma'am. It's clear.
Okay. You've got the Jacobian matrix. Now let us try to see how it has been coded in Matlab. So in Matlab, what I've written is you have written a function. What happens is earlier the function only returned the function value, right? Now what happens is the function will return the Jacobian also to you. So what happens is you are given the function from the function. You have given the x value. From the x, the first value is x, second value is small y, the third value is small z. We extracted x, y, z. Function values are written as a column. Now the Jacobian has to be written as a matrix. The first row is 1 minus 1 0. Second row is 2 minus x z minus 1 minus x. And the third row is y x and minus 3. Just like what you solved it in the PPT. Okay, so this is the Jacobian matrix. So if you have an x, y, z value, you will be getting a numerical data for this. Okay, I'll show that. So now how do you run this? Just a second. Yeah. For running this, what I do is first I give an initial value. Let my initial value be 1, 1, 1. Okay, I'll run this for initial value 1, 1, 1. I'm running it for maximum iteration 50. Rest everything remains the same. My old new x is equal to x0, x old is equal to x0, just like I did earlier for my Newton-Raphson. I can run it for max iteration 50. Okay, this is my, I'm using for a particular x, I look at the Lorentz function. So I'll run this code for you. I'll show you what will happen to f at j. Okay. So x is equal to x0. Now I'll run this Lorentz function. I get it like this. For this particular value of x, that is 1, 1, 1, f value is this, f1 is this, f2 is this, f3 is this, and this is the Jacobian matrix. Okay. When I substitute values 1, 1, 1 for x, y, z, this is what I get. Now what I do, this is my update formula. New old x minus inverse of j. This is inverse is the Matlab function for calculating inverse of a matrix. Inverse of j multiplied by the function value. I get the new x. So I started from 1, 1, 1. My new x value is 2, 2, 2, 2, 2, 1. Okay. I calculate the error. Error will be a vector. Okay. Just a second. Oh, the Matlab doesn't know what error an I is. Okay, let I be equal to 1. So my error is x old minus x. So again, I'll be getting as a column. Now I update the old x value to the new x value. I check whether the error is below the tolerance. Now, while checking this, what happens is it checks every element of error. All 3 errors has to be below the tolerance. Only then it will break. Okay. Now I keep continuing this. For 1, 1, 1, let's see what solution I'll get. Okay, you can see this was my first error, 1, 1, 1. If I open this error value, you'll see this was the first iteration. Second iteration error again dropped. Third iteration, fourth iteration, and fifth iteration, it became e raised to 0, 9, minus 0, 9. So it exited the loop. Now my X values are, yeah, capital X values are 1.732, 1.732, 1. Okay, I'll run it for the next initial guess. That is -1, -1, 1. I get the other root, -1.732, -1.732, 1. Now using the next initial guess, -1, -1, 1. Again run it. I'll get the root which is almost equal to 0. Is this clear? Any doubts? Any doubts so far? Yeah. Okay. If there are no doubts, I think these are the things that were taught in the recorded lectures. I hope everything is clear. In case of any doubts, you can just ask me right now. I'll explain any part again. Or else we'll go to the problems. So here I have like 4 or 5 problems. What I'll do is I'll give you this question. Please open your Matlab and try to code this. If you don't have a Matlab access right now, what you can do is either you can use online Matlab or else just take a pen and a paper and try to write the lines of the code. Okay. Once you've got the answer, please put it in the chat box. Okay. Once I see that sufficient people have done it, then I'll discuss the answer. Even if you don't get the answer also, it's completely fine. But please do try it because it's like a coding class. So unless and until you try doing the coding yourself, you'll not be able to learn the subject. Okay. So first I'll show the first problem. So this is a Newton-Raphson. You can go read the problem again, but what I'm telling is what all you need to answer is you need to see that after the first iteration, what is the value of the variable, and in the first iteration, what is the error. So you have to also repeat the same thing for the third iteration and the fourth iteration. So basically, this Newton-Raphson, you have to run it for like almost 5 iterations. You have to run it, and you have to tell me what is the value of the variable and what is the error that you get for each of the iteration. Okay, so this is what is intended to find. I'll just give you a few minutes. Once you get the answer, please to put it in the chat box. Okay, then we'll discuss. So this is the problem 1. Any answers? So let's try to solve this problem. So this is a Newton-Raphson equation. You have given the function and you have given the derivative of the function also. Okay, you need to start from the initial guess. T of 0 is equal to first iteration. The initial guess is 10. So you need to use the Newton-Raphson equation. So first iteration, you need to find what's the value and you need to find the error. You have to repeat it for the third and the fourth iteration. Now let's look at the problem. So this is your, I am only running it for 4 iterations because in the question I've only asked for the values till 4 iterations. I can run it for many iterations also, that is completely fine. I'm giving a tolerance level of e raised to minus 4. This is not needed actually, but if you want, you can give the tolerance. Now I'm running it for 4 iterations. I've written a function fun1. What happens is if I give a value t here, it will give me the function value and it will give the derivative value as output. Okay, I get the f1 and df1 as the outputs. Now what I do is I give a particular value of t, I get the function value and derivative value, and this is the Newton-Raphson update. That is t minus f divided by d of f. This is a Newton-Raphson update, t new. I calculate what is the error, that is absolute difference between t new and the old t. I update the value here. So I just save the values, okay? T new, I just save the value. I have the error tolerance check and I update the value of t. Okay, so what happens is at every iteration, I am saving the value of the t here in this variable x, and I'm saving the error here in this error value. Now clear? So you'll see. I'll just run this code. So you will see the x actually, for the first iteration, my value is, after the first iteration, my value is 18. So I started from 10, right? From 10, I got to 18.45, then it became 17.25, 17.21. Finally, I lasted in 17.2198. And my error after the first iteration, it was 8.45, it became 1.208, 0.035, and later it became 2.7080 e raised to minus 0.4. So now I have to just display. So my first is I have to display of the first iteration what happened. So after the first iteration, it will be num to string. This part I've already explained how to use the display command. Display and it's the same thing. Okay, it is not difference. Disp t1 is num to str, the first entry of x. And the error is first entry of error 1. And in the third iteration, it will be the third entry of x. And fourth iteration, it will be the fourth entry of x. And the error in the fourth iteration is error fourth entry. Okay, this is the strings. Numeric data has to be converted into string using num to str function. And you have to put the entire string in a square bracket. Okay, for example, I can just show the square bracket here. What happens is this. You get a string like this, and that will be displayed. So this is what you get. T1 is 18.457, error was 8.457, and the T3, the value is 17.2198, T4 is 17.2198, error is of the order of 2.708 e raised to minus 0.5. Do you have any questions, any doubt in this problem, any part of the problem? If you have any doubts, please do ask me now. If anybody had tried this question, have you got the similar answer? Okay. Since I'm not getting any questions, I hope you guys have understood. So let me just move on to the next question. This is the next question. It's a fixed point iteration. Don't get confused by all these things. So here we have a ideal gas equation. Okay. Ideal gas equation is written by this V is equal to RT by P. But instead of this, let's look at the Peng-Robinson equation of state. So that is like this. V is equal to RT by P plus B minus A, V minus B, all these complications. You can see that V is there both in the LHS side and in the RHS side, V is there. A is a constant, B is a constant, R is a constant. T is also a constant, 321 Kelvin. P is also a constant, 20 angstroms. Okay, all the variables are given to you. You have to iteratively start. Okay, so you have to start with an initial guess and you have to find what is the final value of V. What all you need to do is compute and report the value V0 obtained by the ideal gas law. So initial gas, you can use this. For the initial value of V, just use RT by P. You will be getting initial value of V. Put that in this equation, go on, continue going. So compute and report the value V0 obtained by ideal gas equation. The first value is obtained by ideal gas equation RT by P. Then use the fixed point iteration and calculate what is V1, first iteration V, second iteration V, and then you have to repeat until the error falls below 0.001. This is what you need to do. I'll give you a few minutes. Try to do it using Matlab and then we'll discuss the answer. Once you've got the answer, you can just put it in the chat box. We'll discuss it. Okay. So your time starts now. Please do put your effort and please try solving this problem. And if you have doubt, please do ask me. Any answers? I've given you enough time and you guys are not letting me like solving, I think. So let me just move forward. So first I've given all the input data R, T, P and all the values. My initial value will be RT by P, just the ideal gas equation. Okay, that is my V0 RT by P. Now what I do is, yes, I've got a reply in chat. Yeah, we'll look at the value. Okay, thank you. Thank you so much. At least one person has been replying. Yeah. So now we have the initial value RT by P. Now what I do is I do the fixed point iteration. Here I can use the convergence criteria, as I said, 0.01. So first time being, I'm just running it for 20 iteration. My V value comes from this equation. This is the exact equation that has been given in the PPT. RT by P, we have all this equation here. V0 will be here. We get the new V1 value. Error is nothing but the error absolute difference between V1 and V0. Then you replace your the old value by the new value. Now, if the error, any of the error goes below 0.01, we stop it and we say that the V converged value is V1I. Okay, this is for just for the sake of printing it. Okay, and then I break the loop. So here I can see that outputs I need is that V0 is nothing but num2 str Vint. That is RT by P. Then I need V1 is equal to, I am storing all the V values in this variable V1. Okay, so at every iteration, this value will be stored. So that is the first entry here. V2 is the second entry here. Now the volume that I get after convergence, I am saving it here. Okay, the final volume. So that will be saved as V converged. So let me just run the loop. When I run, the initial value that I'm getting, our RT by P is 1316.1. Using ideal gas equation, this is my initial guess. After the first fixed point iteration, I get 1216. After the second fixed point iteration, I get 1206. Finally, when the volume has converged to the threshold of 0.01, I'm getting 1205.8135. Yeah. What, whoever, I don't know, it's been the name I can't understand. It's some Realme somebody. Okay, who have answered the in the chat box, you've got the right answer. Yeah, good. Okay. So when you guys give me the answer, I get an understanding, okay, of whether you guys have understood the class or not. Okay. So yes, the answer is correct. So let's move on to the next question. I want everybody to answer, okay, in the chat box. So this is a multivariate F-solved question. You have two equations. Remember to give these two equations as a column vector. Now D3 is a constant equal to 3. X and Y is the only variable here. Initial guess of X is 4. Initial guess of Y is 8. You have to use F-solve. Remember, you have a column vector of functions. Then you have a Jacobian. You have two functions, two unknowns. So your Jacobian will be a 2 by 2 matrix. Okay, try. Okay, you don't have to worry about all that in F-solve. You have to directly, you don't require a Jacobian. Sorry about that. In F-solve, you have to just give the two functions as a column vector. Separately write a function and let me know the answer. I'll give you like 2-3 minutes. And once you've got the answer, please put it in the chat box and then we'll discuss. Any answers? So let's discuss the answer here. So F solve, you have to first give the two equations, right? So, so the initial guess it is 4 and 8. So F solve, the solution will be saved in this variable X solve. I call the function F solve. It is a variable in X. So I've written a function called fun3. So this is what the function does. It takes in a variable and it has, I'm taking the first variable to be small x and the second variable to be small y. D is a constant, so I'm just writing D equal to 3. And this is my first function. Remember, it has been written as a column vector. So it will be 1, 1 and 2, 1. One column, two rows. First function will be the D 12 minus y 80 minus 80 xy divided by 50 plus y. Second function is 0.60 plus 1.5 minus 60 y divided by 50 plus y. So these are the two functions. So straight away I give the function here and the initial guess here. Let me run the code. I'll be getting equation solved and the answer for the first variable x is 6.197 and the second variable is 2.910. Any doubts in this question? If you don't have any doubts, let's move on to the next question then. It's the velocity of a rocket. You have an equation here. V is equal to u0 L log of m minus qt, m by m minus qt minus gt. U0 is a constant. M is a constant. Q value is also given to you. G value is also given to you. So the only unknown is V and T. Okay, so for a particular value of T, you will be getting a particular value of V. Now it is, we wish to find the time at which the rocket reaches 500. So V is also given 500. So the only unknown is time. We need to find the time at which the velocity is equal to 500. Now you have to use the F0 because it's in a single variable, only time is a variable. And F0 and the bracket is between 25 and 100. The bracket for time is 25 and 100. Here, one tricky part is there, which I'll tell you. Always in this, when you're writing the function here, it should be in the form of f of x is equal to 0, right? But here you don't have a format f of x is equal to 0. So what do we do? Just give me a second. Any questions? Just give me a second. I just got disconnected. So here in this, what we have to keep in mind is that you have to always write the function in the format f of x is equal to 0, right? But here you have something like this. So it is written as 500 is equal to some f of x. This is how the function has been written. B value is 500. So you have to write it equating it to 0. What do you do? One way is take the 500 to the other side. You can write the whole equation f of x minus 500 equal to 0. Now this becomes your function. So now what you do, you write rocket fun in such a way that you code this g of x. So that is the whole term minus 500. Or else you can write 500 minus also. That will be equal to 0. That's how we have to code it. Okay, this is a small tip. I'll not erase this. So just, this is a very easy portion, a very easy question. You can just finish it in like few minutes. So I'll just give you like few minutes and then after that we'll discuss the answer. Any answers? So let's go to Matlab. So this is a function. Yeah, got one answer, 89.8122. Yeah, I've got one more answer also. Let's see if this answer is correct. Okay. So first we have all the constants u, m, q, g, and everything. And this is how the function value should be. So as I said earlier, this is the function that is given to you in the question, right? So you have either you can do this function minus 500 or 500 minus this function. Okay, that is not a problem because ultimately this has to goes to zero. So here I'm writing 500 minus v as my function. That will be the output of this rocket fund. Okay, not this function. You have to subtract 500. That will be the output of this function. Now what I do is this is the 25 to 100 is the syntax that has been given to me. Okay. The solution that I get is 89.8121. Yeah, you've got the answers right, both of you. Ananda Krishnan and whoever this person is, Realme RM X211. Okay. So both of you have got the right answer. And let us check what is the function value at 25. So what happens is you have to just give 25 the value here. It will give you the value, function value there. So the function value is 4.483. Yeah, 25 minus. Somebody have got the answer. I think, I don't know what was mentioned. 25 minus. No, the question was a t equal to 25, right? So what you have to do is you have to subtract t, have to put, in this equation, you have to put t equal to 25. Okay. So here you have the u values. Let me write the values here. U values you have t equal to 25. So your v value will be, your v value is 51 point something. Okay. This has to be subtracted from 500. Yeah. Yeah. This is the value you get. I think, yeah, it's almost similar. The actual answer is 4.48342 e raised to 02. Okay. You've got that answer also correct. It minus and plus, that depends. Okay. Minus doesn't have any negative time, doesn't mean anything. So, sorry, it's not negative velocity. Okay, negative velocity doesn't mean anything. It just only means that the direction has changed. Okay, so negative and positive is not a problem. Absolute value will be something 4.48 something. Now, moving on to the next problem. This will be the last problem of today. You have seen a tank here, a cylindrical tank, and the velocity, water velocity of the water is v meter per second is discharged from a cylindrical tank. The equation is given to you. G is a constant. H initial head, you don't know initially. It is tan H, okay? And you have square root of 2gh divided by 2l. And what all do you have? L is given to you, time is given to you. So the only unknown is H. V is a function of H, okay? So now first what we have to do is, for different values of h going from 0 to 4, you have to plot f of h. Okay, you have to plot this function. Okay, that's the first part. Next is use bisection method. And with the limits are given to you, xl is equal to 0, xu equal to 4 meters. The initial head needed, velocity is also given to you, 5 meter per second. Okay, velocity is 5 meter per second. Length is given to you, time is given to you. You have to calculate what is the value of h. Okay, h, it should fall between the brackets 0.4, 0 and 4. And this is a convergence limit that is given. You have to compare the same result using Matlab's F0 function. So this is a bit longer question. Try to do at least the first two parts and then we'll discuss the answer. Since we have already reached 8 o'clock, I'll discuss the answer. So first is we have to plot h from 0 to 4 and you have to plot this function. Okay, function versus h. Let's see that. Okay, I've got an answer. H is equal to 1.465. Okay, we'll check the answer. Just give me a second. So all 9, L length, everything is given. And time, it has to be in seconds. I'm not sure if you have converted into the right units. Just make sure like whatever quantities have been given has been converted. See, G is in meter per second square. So everything has to be in seconds and length has to be in meters. So now H is, you have to plot from 0 to 4. So I'm right now using linspace 0 to 400 entries. You can also use what you say, the colon operator. That is also completely fine. This is the function that I have. Square root of 2gh tan h square root of 2gh divided by 2l multiplied by t. Now I am directly plotting it. So once I plot, this is what I'll be getting. I'll be getting a curve like this. This is initial head h, velocity v. Okay. H going from 0 to 4. This is how my function looks like. Okay. That's the first part of the function. Now moving on to the second part. I've written a separate function for that using bisection. Okay. So this is all the constant. L t equal to 2.5. Target of v is 5. Okay. So this is similarly what we did earlier. We have our equation is v equal to something and v is set to be 5. But whenever you're using this function in the methods that we have discussed today, it should be in the form of f of x is equal to 0. So you have to subtract this. So you have to subtract this portion. Only then the function value will be getting. So your lower bound is 0, upper bound is 4. You calculate the function at lower bound, calculate the function at upper bound. See if the signs are opposite. Okay, if signs are the same, it is like a initial guesses is wrong. If the signs are opposite, then everything remains the same. You run it for 50 iteration. You calculate the error between the upper bound and the lower bound. Your new value is the midpoint of the upper bound and lower bound. You calculate the new function value. Check the signs of the new function value. If it is greater than 0, means that both have the same signs. So then FL is replaced by XL. F new is XL becomes the X new and FL becomes F new. Otherwise, XU becomes X new and FU becomes F new. And when do you break the loop? You break the loop when the error falls below the threshold given in the question. Okay. So that's the part. So let's just run this part of the code. I'll just select this. Okay. And I'll run this. I'll be getting when initial h to achieve 5 meter per second velocity in 2.5 seconds and L at 4 meter should be 1.2749. There's a slight difference in the value. Just check your solution with the solution that I've shared. Okay, just check if there anywhere you have gone wrong. This minus 5 is very, very important. Only then you will be getting the function in the form of f of x is equal to 0. So the final answer is 1.2749. The same thing we can look at with the f0 function. In the f0 function, the function should be this square root minus v target. Okay, that should be there. Minus that v should be there. That is the function that we are looking at. You can write separate as a Matlab function or else you can write it directly here. Okay, and as an anonymous function. And h initial is equal to f0. The function part, this part will come here directly. And you will give the lower bound and the upper bound. And running this part, you will be getting again h initial to be 1.2749. Okay, that's the answer you'll be getting. Both answers are the same. This is what you get using the bisection method, and this is what you get using the f0 method. Any doubts in this question? I'll just go through the code once again. In case you want to take a screenshot, you can do that and compare your answers. Bisection rule. And this is using the f0 part. Any questions? Okay, I hope it's clear. That was the last question of today's session. So if in case you don't have any further doubts, you can leave the session. We'll meet again next Friday, 6 to 8 p.m. We'll be discussing the next week's problems. So that's it. As there are no more questions, I'll be ending the session now. And the recording will be uploaded in YouTube, and I'll be sharing the link through the Excel sheet that is shared with you. And the PPT will also be shared. So thank you so much for attending, and special thanks to all the people who actually were involved in this class and tried to solve the questions. Okay, yeah, thank you so much. I hope the session was useful. So let's meet again in the next week, next Friday. Okay, yeah, thank you all. I'll be ending the session now.